Now I am going to explain very important part. Second type of imperfection, and it is impurity defect. And children, so you know, impurity means some foreign material has been added, and this defect creates so many remarkable changes in the behavior of solids. For example, if you take NaCl as main substance, NaCl or any monovalent. Main substance must be having monovalent cation, and the impurity is divalent. Impurity is divalent cation. Like you can have CdCl2, or here you can have AgCl, either NaCl or NaCl or anything can be taken. In place of CdCl2, you can have CaCl2. But you have to keep in mind that this is the impurity. This is the impurity. And how it is caused? How it is caused? Now see, here there is the lattice. In the normal condition, let it be the first cation, there be the anion, then there is the cation, here there is the anion, then cation, then here anion, here cation, here anion, and here cation. Let this be the normal condition. This is what we say, this is lattice of monovalent cation. Now impurity of suitable type is added. Now you know sodium, it has +1 charge, cadmium, it has +2 charge. So if we remove one here, and if you remove one from here, and so here there is the cationic vacancy, here is the cationic vacancy, and in place of this, here comes the divalent. Here comes the divalent cation. So what we can say? The charge is balanced. Here the effect is charge is balanced. Charge is balanced. How charge is balanced? Because sodium has +1. So 1 and 1, 2 have been lost from the lattice position, and in place 1 either in interstitial position, or it depends on the size. It can occupy either way, either at the lattice point, original lattice point, or in the interstitial position. So charge will be balanced because it has 2 plus, here 1. So 2 have been lost, so it is same. Now second point will be density. Density will be decreased. There will be decrease in the density. So this type of defect is called as impurity defect. This is very important part, that is metal excess due to interstitial cation. And this is when children, when we take the zinc oxide, and so zinc oxide on heating, it has the zinc ion. Here there is the formation of oxygen gas, and here of course electrons are released as per the reaction. So the oxide is broken to zinc ion and this oxygen, and so it is due to interstitial cation. So what happens? It is metal excess. Think logically, it is metal excess. And again, when we see, there is the cationic, anionic. And so here this metal excess, zinc, as the oxygen is lost, so zinc electrons, they are also lost. So electrons position is captured by some of the zinc ions here, and this position it is taken by the electron. This position of this here zinc, there is the zinc is not a percent, so it becomes excess indirectly. So it remains as it is. All the cations remains as it is, but the electrons they occupy the anionic. So electrons occupies the anionic position, and as a result, as we are heating at high temperature, so it appears yellow. This is very important point, that zinc oxide on heating appears yellow. Why? It means in normal condition zinc oxide is white in color. Now coming to second very important part, non-stoichiometric point defect. So non-stoichiometric, as you know, when the stoichiometry is not maintained, when the stoichiometry is lost, that is, the solids are not symmetrical. Solids are not symmetrical, and it leads to different properties, and it is again of the following types. And here first is the metal excess defect. This is very important point. Metal excess defect, children. So when the amount of metal, when the percentage of metal, when the quantity of metal is more, and it results into different properties. For example, if we take any alkali metal halide, preferably we take the colloids because colloids are moderately stable. So NaCl and sodium vapors, or KCl and K, and lithium fluoride and lithium. We can take any one of the pairs. So NaCl, KCl and K pair has to be taken. So when it is heated, it results into particular color change. Because of something very important property, and it is called as F center. F center. Now this F center, actually it is due to anionic vacancy. It is caused due to anionic vacancy. How it happens? We are heating NaCl. So on heating NaCl, there is formation of suppose balanced, and sodium ions are produced, and here chlorine gas is given out, and here we are heating with Na gas we are taking, and so if we draw the lattice here, again the same pattern, plus minus and minus. So this is going to take place here. Now if any of the position is lost, and here this position is captured by the electron, this position is captured by the electron, and the electron, it is being heated at very high temperature. So due to heating at very high temperature, the electrons are very small particles, so electrons are excited to higher energy level, and they start vibrating to the corresponding frequency, and here it appears yellow. This is a very important point to note, that when NaCl is heated with sodium metal, it appears yellow because the electron present, it starts vibrating with a frequency which corresponds to yellow color. Similarly, this potassium. Now this is last part of non-stoichiometric point defect, children, and so it is called metal deficiency defect. And this metal deficiency defect, as name indicates, metal deficiency. So the density of the solid is decreased, and this is one point. Other point is that it is feature of the compounds. It is property of the compounds or the solids having variable valency. So it is important to know, it is feature of the solids having variable valency. This is very important point to know. Valencies are variable, so such solids can exhibit this type of valency, and the equal number or required number of the ions they exhibit, they contribute in such a manner that the solid's identity is maintained. Like, see, we write Fe3O4, but it is technically, in terms of chemistry, it is not correct. And Fe3O4, it is equal to how much? It is equal to FeO and Fe2O3. How? Fe, see the valency. Here iron is in oxidation state of 2 plus. Here iron in the oxidation state of 3 plus. So this type of example is there. And how they will be equalized? That 3 ferrous ions or Fe2 ions, they are equal to 2 ferric ions. So see here, 3 2s are 6 and 2 3s are 6. The charge is balanced. Here, the charge will be balanced. Charge will be balanced. This is one point. But the density will be decreased. There will be decrease in the density. And so this is very important point to note. And as a result, this compound, this substance will have some other property. Now, other example in this is FeO. FeO, it is commonly called as oostite. It is not a pure solid. It is also an impure solid. And so, what do we mean? That here, in this, there is Fe2. And oxygen, it is in form of oxide, it is 2 minus. But again here, some of the Fe2 ions are replaced by Fe3 ions so as to maintain electrical neutrality. Electrical neutrality is maintained. So Ustaite is better written as Fe 0.930 to Fe 0.960. So again here the variation is not same. It is minimum 0.93 and maximum 0.96. So deficiency of 0.4 is there, and so it will be compensated by what? It will be compensated by ferric ions in sufficient number to make the solid electrically neutral, and density will be decreased. So this is very important point, and the other points are ferrites are also there. Ferrites are there, in which the ferrites and aluminium is there, silicon is there. So children, there is a change in the electrical property also, some other properties also changed.